When we talk about reinforcement learning, usually we're picturing an agent learning through trial and error, right? But what if it didn't have to? What if it already started with a perfect map of its world? Today, we're diving into planning, the art of finding the absolute best path when you already know all the rules of the game. Okay, so picture this. A robot's in a maze. But here's the twist. It has a perfect, detailed map that shows every path, every dead end, everything. It knows the game completely. So the problem isn't about exploring or learning anymore. It's about pure planning. How does it figure out the absolute best path from any point? The answer lies in a really powerful technique called dynamic programming, or DP for short. Now, the name might sound a little intimidating, but trust me, the idea behind it is actually beautiful in its simplicity. DP is all about solving huge, complex problems by breaking them down into smaller, bite-sized pieces, solving those, and then stitching the solutions back together. Now, for DP to work its magic, a problem needs to have two key ingredients, something called optimal substructure and overlapping subproblems. And luckily for us, the frameworks we use for these problems, called Markov decision processes, well, they have both of these properties baked right in. So, what is optimal substructure? It's actually a really intuitive idea. Think of it like this. The best route from New York to Los Angeles has to include the best route from, say, Chicago to Los Angeles. In reinforcement learning, the Bellman equation is what gives us this property. It lets us figure out how good a starting point is by looking at how good the next possible steps are. And overlapping subproblems, this is even simpler. It just means that while our robot is planning, it's going to need to calculate the best path from the same exact spot over and over again. Instead of redoing that work every single time, we can just solve it once, write down the answer, and look it up later. In RL, the value function is basically that notepad. It stores the answer for us. Okay, so we've got the foundational ideas down. Let's put them to work. The very first thing we can do with DP is evaluation. If our robot already has some kind of plan, we call that a policy. How do we figure out exactly how good that plan is? This is what's known as the prediction problem. We have the map of the world. We have a policy, let's call it pi, which is the robot's current strategy. Our goal is to calculate the value function, v pi, which is basically a number for every single spot on the map that tells us, here's the score you can expect to get from this point forward. And the key is turning that big, scary-looking Bellman equation into a simple update rule. Don't get bogged down by the math. Just imagine every square in our maze starts with a value of 0. Then we do a sweep, updating each square's value based on what its neighbors are worth. We just keep doing these sweeps, and with each pass, the values get more and more accurate until they finally lock in. And here's exactly what that process looks like. In this little grid, every move costs 1 point. We start out at k equals 0, all values are 0. After one sweep, boom, every square is now worth -1. But on the next sweep, the squares start to factor in their neighbors' values, and you can literally watch this wave of information spread across the grid until the numbers stop changing. Awesome. So now we can take any plan and give it an accurate score. But that's only half the battle, right? The real goal is to find the best plan. And this brings us to our next big idea, policy iteration. It's the logical next question, isn't it? If you can calculate the score for your current strategy, what's the next step to finding an even better one? The answer is this really elegant two-step process. It's almost like a dance. First, you evaluate your current policy. That's the step we just learned how to do. Then, for step 2, policy improvement, you go to each spot on the map and look around. You ask, if I did something different here, would it lead me to a higher value spot? If the answer is yes, you update your policy. You just act greedily and take the better move. And here's the powerful part. By repeating this dance of evaluate, then improve, our policy is guaranteed to get better, or at the very least stay the same. It will never get worse. And if you keep doing this cycle, you are mathematically proven to eventually arrive at the single best optimal policy. Policy iteration is fantastic, but that evaluation step can sometimes take a lot of sweeps. So you might be wondering, is there a shortcut? And yes, there is. It's called value iteration. Value iteration is built on something called the principle of optimality. It sounds fancy, but it's really just common sense. It says that if the best path from Seattle to Miami goes through Dallas, then your route from Dallas to Miami must also be the best possible route between those two cities. Any piece of an optimal path has to be optimal itself. So how does value iteration use this? Well, instead of that two-step dance, it just cuts to the chase. It combines the evaluation and the improvement steps into one single efficient update. And it does this by using a slightly different equation, the Bellman optimality equation. The key difference is right here in this little max operator. Instead of just calculating the value based on a fixed plan, each update immediately asks, from this spot, what is the single best move I can make? It looks at every possible action and just picks the one that leads to the maximum value. The greedy improvement is baked right into the value calculation. And this process looks like waves moving backward from the goal. We start by saying the goal's value is 0. In the first pass, any square that's one step away from the goal gets a value of -1. In the next pass, any square one step away from those squares gets -2. The optimal value, the shortest path, just spreads out from the goal like ripples in a pond. Now this highlights a really important conceptual difference. Policy iteration always keeps a complete logical plan at every single stage. Value iteration, though, is laser focused on just finding the best possible score for each square. The scores it calculates along the way might not make sense as part of a single strategy. Only at the very end, once the scores are final, do we figure out what the best path actually is. Okay, so we've covered two powerful algorithms that both get us to the same optimal solution. Let's just put them side by side to really lock in our understanding. Looking at them like this, the differences are pretty clear. Policy iteration is that two-step dance. It uses the Bellman expectation equation, and it always maintains an explicit policy. Value iteration is the shortcut. It uses the Bellman optimality equation in a single update step, and it's all about finding the optimal value function first. But here's the catch with both of these methods. They're what we call synchronous, which is just a fancy way of saying that in every single pass, they have to visit and update every single state on the map. Now that's fine for a small maze, but what about a problem with billions or trillions of states, like the game of Go? Sweeping through every single state just becomes impossible. So what's the big takeaway here? Dynamic programming is an incredibly powerful set of tools for planning. It absolutely guarantees you can find the best strategy, but it only works if you meet one huge condition. You have to start with a perfect map, a complete model of the world. And that, of course, leads us to the final huge question. This is all great if you're a robot with a perfect map, but what happens in most real-world situations where we're flying blind? What do you do when you don't even know the rules of the game? Well, that's where the rest of reinforcement learning comes in, and we'll tackle that next time.